Lebesgue Academy, and today we want to look at Riemann Integral. Riemann Integral is a key integral part that we normally use in both measure theory, and this is in both applied and pure mathematics, so they are very key. So if you have not subscribed to this channel, kindly subscribe to Lebesgue Academy and also share with your friends on about this channel. This is Riemann. We are going to look at Riemann integral. So let f be this function from a closed area, closed interval AB to the little set, and be unbounded. And our key interest here is not that it must be necessarily be continuous function, and it must be on a compact. That means to be closed and bounded interval, in a compact interval that's closed and bounded interval. And we will define what it means for f to be Riemann integrable on a closed set AB, closed interval AB. And in that case, define its integral. So this is what we'll be interested in throughout this discussion here. We'll be able to define what it means for f to be Riemann integrable in a given closed set, closed interval, and also we define the Riemann integral. This is the key definition of Riemann integral. So the integral of f on a given closed interval AB is a real number, whose geometrical interpretation is seen earlier under the graph y equal to the fx, for fx lying in between the interval. This number is also called definite integral of f. So you can divide as area under the curve or the definite integral of the function by integrating f over an interval ax with varying right end points. We get a function of x which we normally call as indefinite integral. So what we'll be doing, we'll be varying the right end point of the interval, and what we'll be getting as the functions of x are what we call indefinite integral of f. Now, the Riemann integral is the simplest integral to define. That's for sure what we need to note. And it allows one to integrate every continuous function as well as some not too badly continuous. So if the function is not too badly continuous, then you'll be able to apply Riemann integral. There are, however, many other types of integrals, and the most important of which is Lebesgue integral. The Lebesgue integral allows one to integrate unbounded or highly discontinuous functions. So the difference between Lebesgue integral and the Riemann integral is that Riemann integral will be able to integrate functions which are continuous and are not definitely discontinuous. But if we talk about unbounded or an island continuous functions, then we need to use Lebesgue integral. We will be forced to use Lebesgue integral. So it will mean that if we talk about unbounded or discontinuous functions, then we will not be able to apply Riemann integral. Remember, this is the Lebesgue Academy, and if you have not subscribed to this, kindly subscribe. And also, if you have any question, leave a comment down there. So the definition of Lebesgue integral requires the use of measure theory. And remember, this introduction to the Riemann integral is actually created basis on introduction to measure theory. So that means if we don't know a Riemann integral, then you will not be able to come up with the idea of Lebesgue, which will now lead us to the measure theorem. So these three are connected. So in any event, the Riemann integral is adequate for many purposes, and even one needs Lebesgue integral. If you really need to use Lebesgue integral by this connection, it is better to understand the Riemann integral first. So if you want to get the idea of Lebesgue integral, which will lead to the idea of what you are calling measure theory, then you need to basically start with the Riemann integral. So remember, our discussion here is basically based on Riemann integral. So kindly follow in every step until the end of this tutorial, so that every bit of Riemann integral you will understand this, because this is key to measure theory. We see that two intervals are almost disjoint if they are disjoint, or they intersect only at a common endpoint. So those are two conditions. You'll say that two intervals are almost disjoint if this is happening almost disjoint. That's not. Either they are fully disjoint or they intersect only at a common endpoint. For example, look at these two intervals here. You'll find they are sharing a common endpoint, which is 1. So this is almost disjoint. But if you compare this and this, you'll say these are not almost disjoint, simply because they don't share any of the common endpoint. They don't intersect only at a common endpoint. That's very key to note. Let's look at this definition. If we let I to be an interval, compact interval, an empty compact interval, a partition I is a finite collection of all L's of almost disjoint and empty compact subintervals whose union is I, whose union is again the interval. So a partition, if you look at this partition here with these intervals here, ik, it's defined by a set of endpoints, that's way to n, and we can now introduce an notation here which we may use partition P either by its interval. So we say P starting for those intervals, or by the set of endpoints of the intervals. These are endpoints of these intervals, x not x or so on. We can just mix them this way. Then we will adopt either notation as for this case, so that we don't have a problem with notations. We are using P here just for the convenience. Okay. So in this context, I think it is clear which one will be used, and there is always one more endpoint interval. Always there is one more endpoint interval is there. So if you look at this example here, we have these intervals here. So you can see in this, the partitions are of 0 of the partition of this interval from 0 to 1. Their corresponding set of endpoints. So this is the P. This is the P. So for this one is the endpoints. First endpoint, second, this way. This way, and 1. So this is now what we are calling the endpoints. So this is now the set P of partitions. Okay. Note that. That's very key. Because what we have tried there, we have tried to use almost disjoint concept. So for this, we note the length of an interval I by this, because actually I'm getting either way at the absolute value of the interval. Note that the sum of this length, which is actually this length, is almost disjoint subintervals in the partition given here. They are almost disjoint in subintervals in that partition of the interval, and is equal to a length of the whole interval. If you sum this, you get the sum of all these subintervals here, and so almost subintervals, then you'll be able to get the whole interval. And this is obviously geometrically or geometrically, and it will follow that this given series here, that if you do the summation of all the intervals, if you expand this, the summations now will follow this, because this first subinterval plus the second subinterval, and so on and so on. Then at the end you'll find this is true, which is basically the interval. So end of the proof. So it will fall automatically like that. If you have any question on either of these points, kindly leave a comment. And remember to subscribe if you have not yet subscribed to this channel. Now, suppose that we have this function, which is bonded function, and again is in the compact interval MB. Then we can define the M, which is the sup or supremum of the function, based on the relation to the interval. And we can even define the infimum, which is M, the infimum of M relative to the interval. Then the partitions of these, if P is the partition of I, then in relation to K, it will mean that the supremum of function in relation to these partitions is actually defined by that, and the infimum of this function in respect to the partition is infimum of F that way. Now, this suprema and infima is obvious when defined. It's a finite real number since F is bounded. That will mean that at any given point, this relationship owns. If F is continuous, if the F is continuous on the interval, then it is bounded and attains its maximum and minimum values on each subinterval. But a bounded continuous function need not to attain its supremum and infimum. So as far as it is continuous and the function is continuous in a given interval, then it will have to attain its maximum and minimum values. And this leads us to the concept of defining what we call the upper Riemann sum of the function f with respect to the partition given here P. So this is the upper Riemann sum of the function, which will be defined by the summation of this. Remember, this is supremum of the function f in respect to the partitions. So it will follow this. And the lower Riemann sum of f will be in respect to the partition P will be given as this. This is actually the infimum of the function of f. Therefore, geometrically, the upper Riemann sum will give you the area of rectangles based on the interval ik, which will lie above the graph f, and the lower Riemann sum is the sum of areas of rectangles which lie below the graph and the graph. Note that this relationship will always be true. This relationship will always be true. Remember, if you have any question on either of these points, kindly leave a comment. If you want some elaboration of either point, you can leave a comment. Remember to subscribe if you have not yet subscribed to Davika Academy. So if you let this pi or phi short, just use pi, denote the collection of all partitions in this given interval, then we will be able to define what we call upper Riemann integral. And upper Riemann integral of f on a given MB will be defined by u function of f infimum upper infimum of P, or the partition in F, which is the collection of all partitions in MB of the upper Riemann sums, These are very key points to note, so call this one. And again, if we use again the same, this one, if the upper integral of all Riemann sums of f is bounded from below, by that. So this infirm is well defined and finite because it's already bounded up and below. And finally, the set of the lower Riemann sums of all Riemann sums is bounded from above by this. And we define the lower Riemann integral by this. Remember, we are using the supremums of the lower Riemann integral. And this is a very key equation too. Okay, so these upper and lower sums and integrals depend on the given integral, closed interval, and as well as the function which is provided. But to simplify the notation, we will show this explicit. A common use alternative of notation of this upper and lower integral is actually defined as this. Of course, from 1 and 2, we are able to see this. Okay. So let's do a definition of this. So abundant function, this is, we say this function is Riemann integral on a given interval MB if its upper integral and the lower integral are equal. In short, if the equation 1 above and equation 2 are equal, then we'll say that function is Riemann integral. In that case, the Riemann integral of f is denoted by this, or this, or this. Either of these will give the proper notations of Riemann integral of the function in a given interval, closed interval. They are same as the one that we have just used above. So this means that if the function is unbounded, then the concept of Riemann integrability will not apply. That's the reason next time we'll be thinking about Lebesgue integration, which will lead us to measure theory. So until next time, kindly subscribe and share with your friends.